All right, physicists, welcome to our April 14th edition of Physics. There is a test this Friday, and the goal of this video is to try to walk you through the basic ideas that we've covered in this unit. So we did Chapter 9 on momentum, Chapter 10 angular momentum, angular notation, Chapter 11 angular momentum, and then Chapter 13 gravitation. And I guess if I had to just make a comment on how this went in class, it seemed that people were most comfortable with this stuff because it's been around for a long time, least comfortable with this stuff because we've just recently covered it. So I guess if I had to use that to try to edit the test, maybe I should focus on the earlier stuff. I'm still thinking that through. Okay, so what did we cover in Chapter 9? Well, we covered the idea of center of mass. If there's no, if you have a bunch of objects and they're only acting on each other and they're all part of the system, the center of the mass does not move. You only have a center of mass moving if you have a movement of the forces outside. This leads to conservation of linear momentum. So if you add up the mass times the velocity of all of your particles, before they interact and after they interact, it should be the same. On the other hand, we also, that required us to define what our momentum is. It's our mass times our velocity. We use the letter little p for that. Be careful, it's not power, it's a vector. Power is just a number of work per unit time. And then the reason that this was helpful is that it helped us to connect forces and momentum. So the impulse, which is the amount of average force times the time, an impulse causes change in momentum. So it causes a change in the mass times the velocity of the particles. So let's see how that works in practice. Okay, here is a 640 Newton hunter gets a rope around a 3,200 Newton polar bear. Okay, so this is, the hunter is about, the mass of the hunter is approximately, if G is 9.8 meters per second squared, if we divide our weight by G, we'll get our mass. So that's about 64 kilograms. The mass of the bear is about 320 kilograms. Okay? And it says they are stationary 20 meters apart on a frictionless level ice. So I can write this as x equals 0. That's the position of the bear. So let's put our bear right there, x of our bear. And then over here at x equals 20 is our x of our hunter. Okay, now if I want to find the position of the center of mass, the position of the center of mass would be 1 over the total mass. So that would be 64 plus 320. So that would be 1 over, in this case, 384. And then here I would have the mass times the position. So that would be 64 kilograms times 0 meters. So that would just be 0 plus. And then here my mass of my hunter, 64 times 20. Okay, so then I use good units in all of this, so it'll be in terms of meters. Okay, so you can go ahead and stick in the numbers. The point is that whatever the center of mass is at the beginning is the same as the center of mass at the end. And so it stays in a position, and you can, as they are pulling, they're pulling towards each other, but that center of mass doesn't change. Okay, so that's the first idea. The next idea was the idea of change in momentum. Now, the point of a question like this is to make you, to force you to grapple with the fact that momentum has a direction. So here I have a mass. The mass is 1.0 kilograms, and we're going to throw it initially at the wall. So the V initial is going to be 1.5. Oh, the V initial would be 2.0 meters per second. And then the V final bounces off the wall, and your V final is going to be, in the way that I've drawn this, it would be negative 1.5 meters per second. Okay, so the only thing I'm stressing here is that velocity has a direction. So plus, minus. Plus x direction, minus x direction. And so when you find your change in P, that would be 1.0 kilogram times velocity final, mv final, minus 1.5 meters per second. And then this would be minus 1 kilogram times 2.0. Okay, so this would be 3.5 kilograms times meters per second. And it would be pointing in the negative. I should have a negative on there. And that just means that it's pointing away from the wall. Now, the thing so this is just a change in momentum. I haven't really done a lot of physics there except to use just the definition of momentum. But the physics portion of this is to identify that change in momentum with the impulse. So whatever average force the wall placed on the ball and the average the amount of time that the ball was in contact with the wall, this impulse is equal to the change in momentum. So the impulse, the change in momentum was in the minus x direction, so the impulse also had to be in that minus x direction, which makes sense. Okay, another example of your impulse momentum theorem. It says a 2.5 kilogram stone is released from rest and falls towards the earth. After 4 seconds, the magnitude of its momentum is, well, what's the force of gravity on the object? It's going to be m times g. Okay, so I'm being sloppy because I'm just doing this on the fly, but this is 2.5 kilograms times around 10 newtons per kilogram. Okay, so that's approximate. This should be 9.8. Okay, fine. So this force of gravity is around 25 newtons. And if you allow that to act for 4 seconds, okay, if I take my force times delta t, then that would be 25 newtons times 4 seconds. So that's around 100 newton seconds. Okay, so it asks, what is the magnitude of the momentum? Well, remember, your force times time equals your impulse. So if you started out with no momentum at all, because it's not moving, and you drop it, that is the amount of momentum that it has acquired through this impulse. So this has to be your answer. It's right around 100, or, you know, yeah, if I use 9.8, I would get my 98. Okay, so we covered our impulse momentum theorem. Next, let's look at our idea of momentum conservation. Okay, so this story has a lady. There she is. Stands on a frictionless level ice with stone. Okay, so the mass of the woman is 64 kilograms. The mass of the stone is 0.10 kilogram. She kicks the stone with her foot so that she acquires a velocity of 0.0017 meters per second in the forward direction. The velocity of the stone is, okay, now take a look at this. This is a perfect problem for conservation of linear momentum because at the beginning, neither the woman nor the stone are moving. So the momentum of the woman is 0, the momentum of the stone is 0. So this is a big old 0 over here. At the end, for the woman, this is positive. For the stone, it has to be negative. Okay, so I know that if I'm adding up two things to get 0, you have to have a positive thing and a negative thing. So that means they're moving in opposite directions. So the lady is going forward. The stone has to be going backward. All right. Now, if she is going forward with some speed, she has a bigger mass than the stone, so I would expect the stone to be going faster than the lady. So it can't be that one. This is plausible. You're going to have to stick it into the in and see if this is in fact correct. I think it is, but you can check. Okay, so this is one where 0 equals mass of the woman, velocity of the woman, plus mass of the stone, velocity of the stone, where the stone is going in the minus x direction. Okay, so that does it for chapter 9. By the way, I'm not going through all of the problems, so I put on the review. So please take the time and actually do the review before Friday because it will be helpful. Okay, so here's your angular notation. There's a lot in chapter 10 where we related our angular and linear coordinates, where we talked about how this v squared over r, that still applies because we still have centripetal acceleration. That's the acceleration pulling us in a circle. But now, instead of just having that type of acceleration, we can also have tangential acceleration. And that's where all of our angular speed and angular velocity or angular acceleration come into play. Okay? And so we copied all of our kinematic equations where we went from x to theta, we went from v to omega, we went from a to alpha. And then we were able to copy some of our physics results where instead of having k equals 1/2 mv squared, we use k equals 1/2 I omega squared. Instead of F equals ma, we have torque equals I times alpha. Instead of the change in kinetic energy equaling work, we have the change in kinetic energy equaling work. Okay, that one seems pretty similar. Instead of power equals force times velocity, we have power equals torque times angular velocity. Okay, so you can see how we're just copying stuff. So, okay, one of the things you're going to have to be comfortable with is doing unit conversions. If you have 1 rev per minute, for instance, that would be the same as 1 rev is 2 pi radians, and then 1 minute is 60 seconds. So there's your minutes canceling out, your radians, your revs canceling out, and that would give you radians per second. Those are good units. Now let's take a look at this type of a problem. It says wrapping paper is being unwrapped from a 5 centimeter tube. So your R is 5 centimeters, and it's free to rotate. Okay, so we're pulling it off like this. So this angular displacement of the tube is going into the linear length of the wrapping paper. It says if it is pulled off at a constant rate of 10 centimeters per second, it does not split on the tube. So V equals 10 centimeters per second. It says the angular velocity of the tube is, well, V equals the angular velocity times the radius. So if I wanted to find the angular velocity, I could just take V divided by R. In this case, that would be 10 centimeters per second divided by 5 centimeters, which would just be 2 radians per second. And there we go. Now, that was just a first step, because once we understand those types of, that type of notation, angular displacements instead of linear displacements, we can start to talk about angular kinematics. And that's just using your constant acceleration model in terms of angular coordinates. So, all right, it says a flywheel rotating at 12 revolutions per second is brought to rest in 6 seconds. Okay, so 12 revolutions per second. Is that going to be omega, theta, or an alpha? Well, remember, omega is radians. Sorry, theta is radians, omega is radians per second, and then alpha is radians per second squared. Okay, so this is displacement, velocity, acceleration. And so if it's 12 revs per second, that means that this is your initial velocity. 12 revs per second, which is the same as, I can change 1 rev into 2 pi rads. Okay, and if you have your final velocity as 0, and that happens in t equals 6 seconds, it says the magnitude of the average angular acceleration. Angular acceleration is which one of these? That. Okay, so you want to find this. You have these three. This looks like a good equation to use. So I'm going to have omega equals omega naught plus alpha t. 0 equals 24 pi plus alpha times 6. Okay, and so you can solve that, and then your alpha would be minus 4 pi radians per second squared. Okay, and it asks for the magnitude, so then you don't have to worry about the 4. All right, there we go. Now, when we go to a little bit more complicated questions and actually involve physics, that is using Newton's law, F equals ma, we have to start thinking in terms of the rotational inertia, or the moment of inertia. I have been inconsistent in the way that I use those terms. I will try to be consistent and just use rotational inertia on the test. All right, so it says 4 identical particles, each with mass m, are arranged in the xy plane as shown. So we got a nice picture. They are connected by light sticks to a rigid body. If mass is 2 kilograms and a is 1 meter, the rotational inertia of this ray about the y-axis is. Okay, so the thing to be aware of is you get a different rotational inertia if depending on what axis you use to spin your object around. So in this case, we would just use this expression where your rotational inertia is your mass times your distance to the axis of rotation, right? This y-axis is your axis of rotation, and then square that distance. So let's look at this one. Our first mass is right on the axis of rotation, and we're just treating these as point masses for the moment. So this would have a contribution of I equals 0. Why? Because r is 0 for that. Plus, let's see, what's our next one going to be? How about this one? Well, that is a distance of a. It has a mass of m. So that would give us a m a squared. Similarly for this is a distance of a away from the axis of rotation. It doesn't, this up and down doesn't matter in this one. So plus ma squared. And then right here, your distance is 2a, so that would be plus, okay, so this one, and then this last one would be m times 2a squared. Okay, so overall your rotational inertia would be 1, 2, this was 4, 2 squared is 4, 1, 2, 3, 4, 5, 6, 6 ma squared, and you can stick in the numbers and find out what the answer is. Now, the thing that's a little tricky to realize in a lot of these rotational motion problems is that it's not, it's a little different from our case where we just had F equals ma and you have an object out in space or something like that. The thing that makes these problems a little weird is that sometimes you have a point that's fixed. So, for instance, in this problem off your review packet, you have like a thumbtack or a nail, and the object is forced to spin around that nail. So there are different types of forces that will not cause any acceleration. So, for instance, this F5 is just pulling in the direction of the rod. And the reason it isn't able to move the rod is just because we presume as a part of our problem that this point is fixed. Okay, so this would cause zero acceleration of the rod. Also, if you're just pushing on that point can't move. So F2 would also have cause zero acceleration of the rod. So that's sort of our logic behind the torque. The torque is if you have a object, doesn't need to be just a line, but if you have a force that you're putting on this. Okay, so here's the distance from the axis of rotation. So this is the point that we've nailed down. It can only spin around that. And you're applying a force, all right? In this particular case, only the part of the force that's perpendicular to that R is going to apply. So the way that this formula works is, you notice there's a angle here between your R and your F. This is the theta that's in the formula. The torque is your RF sine phi. And the thing to notice about this is that this type of a force would cause your object to spin in the counterclockwise direction. From our right-hand rule, that's considered positive or out of the page, but I don't need you to focus on that. What I need you to focus on is what direction would it cause it to spin. Because if I had a different force in a different direction, for instance, this could also cause my object to spin in this direction. And so if I use my R cross F, that would also be out of the page. So if I had these two forces as my only two forces, their torques would add together. On the other hand, if I had a force that was over this way, it's trying to get the object to spin in the opposite direction, and the torque would then be R cross F into the page for that. Okay, so that's sort of the logic. Now, here they want you to rank the forces according to the magnitudes of the torque. Well, F2 and F5 are 0, so F2 and F5 tie, as it says, from least to greatest. So F2 and F5 tie. I can cross off all the ones that don't have that. Then F4, yeah, because that's not at a 90-degree angle. The biggest torque comes when that phi is equal to 90 degrees. Then Okay, then F4, yes. And let's see. Then F1 and F3 tie. Yeah, they do tie because they're both the same distance around from the axis of rotation. They have the same magnitude of the force. The only difference is the direction. So this one would try to get the object moving counterclockwise. This one would try to get the object, F1 would try to get the object, the bar to spin clockwise. F3 or F4 would try to get it to spin. F1 is clockwise, F3, F4 are counterclockwise. So F3 and F4 are torques out of the page, F1 is a torque into the page using your right-hand rule. Okay, so Newton's second law, if we go ahead and use our form of Newton's second law for this angular stuff, it says we have a disk with a rotational inertia of 2 kilograms times meter squared. So that's your I. And a radius of 0.4 meters rotates on a frictionless axis perpendicular to the disk faces and through its center. A force of 5 newtons is applied tangentially to the rim. Okay, so the force is 5 newtons, but what we want is the torque. But in this particular case, it's easy because they say it's tangential. That phi angle will then be 90 degrees, and our torque will just be 5 newtons times 0.40 meters. And then that torque would be I times alpha. Okay, so you get to find that alpha, and if you put in this torque is in good units, this I is in good units, and you can go ahead and solve for alpha. So to my mind, this is a very fair question, and I would expect to see something very similar to that on the test. All right, now a torque of 170 Newton meters does 47. Okay, so once we've done our F equals ma type of thing, now we can move on to ideas of energy and momentum, just like we did with our linear motion. So in the first case, we have our work energy theorem, which is that our final kinetic energy minus our initial kinetic energy equals the amount of work that we put in. So it says a torque of 170 Newton meters does 4,700 joules of work on a rotating flywheel. If the flywheel's initial kinetic energy is 1,500 joules, what is its final kinetic energy? Well, in this case, the final kinetic energy would be just whatever you started out with plus the extra work that you put in. Okay, so 4,700 plus 1,500, and there you go. Easy peasy. Now let's think about putting power into a system. It says a torque of 470 Newton meters acts on a flywheel. At the instant that the flywheel's angular speed is 56 radians per second. Okay, angular speed, what variable do I use for that? I use omega, 56 radians per second. It asks, at what rate is work being done? Okay, rate of work, that should say power to you. Reminder, P here is power, not momentum. So we're given that we're given the omega, we're given the torque, 470 Newton meters, and if we have those two things, we can find our power. Okay, so just take one, multiply by the other. In this case, the way that I would do it is to say, oh, this is about 500, this is around 50. Okay, 0, 0, 0. So I know that my answer is going to be somewhere around 25,000 watts. This is the only one that's close. And that's my answer. Okay, so as we said, we set up all of our notation. We got to the point where we could do kinematics with rotations. We got to the point where we could do things like work, energy, power. Our last piece here is to apply ideas of momentum to this. And one of the little hiccups is that for rolling discs, it's a little strange, because as the ball, if you have rolling without slipping, the axis of rotation is essentially the bottom of the wheel. But that's a very inconvenient way to do your calculation. So if you want, you can also write the kinetic energy, instead of being as a rolling motion that's revolving around a constantly changing axis of rotation, you can instead write it in terms of the spinning kinetic energy plus the translation kinetic energy. So it's moving forward at some speed, and it's going around at some rate, and if you add those two together, you can get the total kinetic energy of the disk. And then the last one is the conservation of angular momentum, which is that if you have a changing moment of inertia, you can get a changing angular speed. Okay, so here's a good example. It says a hoop rolls with constant velocity without sliding along a level ground. Its rotational kinetic energy is at half the same, twice, 4 times, or 1/3 of the translational kinetic energy. So what you need to realize here is that what they mean is the rotational is that 1/2 I omega squared part. The translational is the 1/2 mv squared part. Okay? Now, okay, I can kind of see this already. Let's put some extra detail into this and try to put it in these terms. So I've 1/2. For a hoop, I can look up what the rotational inertia is. It's just m times r squared. Okay, and then my omega, you'll remember omega equals v over r. So I'm going to put that in, v over r, and we're going to square that. Okay, so this is 1/2 mr squared v squared over r squared. Notice that this r squared cancels out with that r squared, and for this particular case, this would be 1/2 mv squared. Now, that's your rotational kinetic energy. We started out with this, we did some work, we found this, and I want you to compare that to your translational kinetic energy. And I think you can see those are the same. So in this particular case, it's the same as the translational kinetic energy. That would not be the same necessarily if you had this as a disk or something like that. So be forewarned. All right, now finally, this angular momentum, most of the problems that I have given you so far have been, cases where, for instance, a fella has his arms raised out, and then he brings them in, reducing his rotational inertia, and then he speeds up, or pushes his arms out, increasing his rotational inertia, and then the rate of his spin slows down. And in those cases, the idea that you're using is I initial times omega initial equals I final omega final. Now, in this particular case, it's a little bit of a tricky one because it's about a man holding a weight in each hand stands at the center of a horizontal frictionless rotating turntable. The effect of the weights is to double the rotational inertia of the system. As he is rotating, the man opens his hands and drops the two weights. They fall outside the turntable. Okay, now you might think, oh, geez, it seems like my rotational inertia dropped. It dropped to 1/2. That's true, but in this particular case, his angular velocity just remains the same because the weights would continue to move this way and that way, and he would continue to go at the same rate. So this is a little bit of a trick question. I will not put a trick question like this on the exam. When you're thinking about cases like the one that we did on our quiz last week was walking towards the center of a merry-go-round. That would decrease the rotational inertia. If you walk to the outside of a merry-go-round, that would increase. So this is the type of problem that I would expect to see on the exam. This one is, I'm going to put a frowny face because there's nothing wrong with it. It's just it's not the most direct way to test your understanding of this idea. All right, and now last but not least, gravity. And so gravity, the most important thing to remember is that if you have two objects, M1 and M2, and they have some distance r between their centers of mass, the gravitational force between the two objects is going to be G M1 M2 over r squared, where G is just a constant of nature, newtons times meters squared over kilograms squared, okay? And the nearer the objects are together, the bigger the force. And that, if you use F equals ma, what you find is that the gravitational acceleration of different objects is sort of independent of the mass. And that's why we can, if you go to the moon, you drop a hammer and you drop a feather, they drop at the same rate because there's no air resistance to stop them. And the masses cancel out on both sides. The accelerations are the same. So here would be a good example type of problem that you might see on a test. It says an object on the surface of the Earth at a distance r from the center of the Earth weighs 90 newtons. Okay, so G M1 M2. So this would be, for instance, the mass of the object, mass of the Earth over r squared equals 90 newtons. Its weight at a distance of 3r from the center of the Earth is, well, the mass of the object didn't change. The mass of the Earth didn't change. All that changes is this distance. We're going from r to 3r. I'll put a big R down there just so we realize we're talking a specific radius. This would be 1/9 times G mass object, mass Earth, over r squared. This, however, is that. So this would be 1/9 times 90 newtons equals 10 newtons. Ta-da! Okay, so the farther you go away from an object, the less gravitational force it is able to apply. The same goes for acceleration. The further away you are from the Earth, the smaller your gravitational acceleration is. So that 9.8 meters per second squared, that is not true for satellites. They are experiencing less acceleration. The further you go out, the smaller your gravitational acceleration due to the Earth is going to be. So in this case, it says Mars has a mass of about, so just to set it up, F equals ma. Okay? For a object near the Earth, that would be your gm, mass of the Earth, over r squared. So your A, so I'm gonna, if you set those two equal to each other, MA equals gmm over r squared, this mass cancels out, and the acceleration is just going to be gm over r squared. So it says the acceleration of a body falling near the surface of Mars, if the mass of Mars is going to be 0.1075 mass of Earth, mass of Mars, the radius of Mars is 0.533 the radius of Earth. All right. So this is if we put in the mass of the Earth and the radius of the Earth, this would be our 9.8 meters per second squared. On the other hand, what we want is, what if we took g times 0.1075 mass of the Earth over 0.533 radius of the Earth squared. Okay, so that would be 0.1075 divided by 0.533 squared times gm over re squared. So this would be times 9.8 meters per second squared. And I'll let you stick that in, and you can figure that out. So that's gravitational acceleration. Now, just to put that in a different way, F equals ma, F equals gmm over r squared. The closer you are, the bigger your acceleration. Okay, so if you have A equals, if you set these two equal to each other, you have an A that's equal to gm over r squared. It says a planet travels in an elliptical orbit around star X as shown. The magnitude of the acceleration of the planet is greatest at point Q, greatest at point S, U, W, the same at all points. Well, no, it's not the same at all points. The reason it's different is because it depends on how far you are. The closer your object is, the bigger the acceleration. Okay, so if you look at the distances to all of those different points from X, your star X, you're the nearest at point W, so the acceleration due to the gravity is greatest at point W. Okay, one last one. It says satellite B is twice as far from the Earth as satellite A. So RB equals 2 times RA. It says, what is the ratio of the orbital period of satellite B to the orbital period of satellite A? Now look, we have already that T squared is proportional, some constants due to mass of the star being orbited, or the planet being orbited, G, which is just a fundamental constant, same for everyone. It's proportional to r cubed. Okay, so in this flavor, we have TA squared is proportional to RA cubed. TB squared is proportional in the same way to RB cubed. And so we can have, it says, what is the ratio of the orbital period of satellite B to A? So TB squared over TA squared would be equal to RB cubed over RA cubed. So this would lead you to TB over TA, you have to take the square root, is going to be the square root of RB cubed over RA cubed. Okay, now TB over TA is equal to, well, RB is just 2 times RA, so it's going to be square root of 2RA cubed over RA cubed equals the cube root of 8, which is the same as 2 square root of 2. Okay, so I know these are a little, the gravitational ones are a little more difficult because you've seen them less. So I encourage you to take some time over the next 2 days and go and try to study as much as you can. Hopefully there were no brand new ideas in this video, but it really is worth your time to do the review sheet. Thanks for watching, and if you have questions, please email me or come to some office hours. Oops.